Welcome to Brain Vision.
Okay, so in this question, we're told that an electric kitchen being insulated with a fiberglass, which is about 4 centimeters thick, right? And we are told to calculate the heat current that flows through this fiberglass when a temperature of 175 is exposed to the one surface of the fiberglass is exposed to 175 degrees Celsius, and then the other surface is exposed to a temperature of 35 degrees Celsius. All right. So the hotter region has a temperature of 175 degrees Celsius, and then the let me say the less hotter region, let's say T subscript C as usual, is 35 degrees Celsius. Not entirely cold, not really cold, but let's just represent with that. Okay, now we are told that the area is 1.40 centimeters squared, and then the thickness of it is 4 centimeters. All right, we can convert all of this to Kelvin, this to Kelvin, this to Kelvin if we want, and this also to meters, very important, and this also to meters. All right, now I hope we know how to do that. So let's take our equation for the heat current, which is equal to K, which is the thermal conductivity times the area per the change in temperature, minus Tc, all divided by L. Okay, good. Now once we have this, we can straight away go on and put it inside the equation. Now the thermal conductivity, this K for the fiberglass is given as 0.040 watts per meter per Kelvin. Okay, so our Kelvin 0.040 times the area, which is 1.40, is in meter squared. I beg your pardon. It's in meter squared. I beg your pardon. This is in meter squared. Okay, all right, let's continue then. So in meter squared, 1.40 into bracket 175 minus 35. Divided by 0.04 meters. Okay, that is the area, let us not forget. Now, when we solve this, this should give us about 196 watt. This should give us about 196 watt. Okay, it should give us about 196 watt. Okay, so that is it. And then the B part of the question is, what is the electric power input to the heating element is required to maintain this temperature? To maintain this temperature, what it means is that the same amount of watts that we have from the heating current is the same electric watts that we have to apply to maintain the same temperature. That is to maintain the same temperature. Okay, so basically all that we calculated over here as 196 watts is the same thing as the amount of electric current, the electric power input required that must be given to the heating element to maintain the same temperature. However, we can still go over and then look at one more thing. So let's talk of the thermal resistance R, which is usually given as the length divided by the thermal conductivity, and it's in the unit of meter squared per Kelvin per watt. Okay, so meaning that this electric power that has to be given to this material will be undergoing some sort of thermal resistance. Okay, so to find the thermal resistance, we need to say that R is equal to 0.04 divided by 0.04, which is equal to 1 meter squared Kelvin per watt. Okay, so this tells us so much that we'll be getting the same thing. Now, this heating current and then the thermal resistance are related in this equation as given us A into bracket TH minus TC all divided by R. Let us not forget that the K and then the L over here flipped around. So since they flipped around, then we have to put in R, remember? This is R. So that is how come we have the equation left like this. So when we put the values in and you solve, that is 1.4 into bracket 175 minus 35 divided by 1, and this should give you also 196 watt. Okay. All right. So there's always some sort of resistance, thermal resistance, to heat that flows through a system. And remember, we want to maintain the same temperature. So the difference in this temperature is what we want to maintain. All right. So since we want to maintain, we do not want to go higher above the required amount of watts we must give out, and we do not want to go below. Hence, the same answer for what we had up here is what